Hello, my name is Simmons, and today I will be answering two questions. First, what is the differential equation? And two, how can we solve them? So, let's start by defining differential equations. So, in the name, differential sounds like differentiation, so derivatives are most likely involved. And the second word, equation, you know what that is. It relates to mathematical expressions, so we are probably equating something to a derivative. This is true, and it turns out a differential is defined as an equation that contains an unknown function and one or more of its derivatives. So, some examples can be functions we've already discussed, such as y prime equals x cubed. This is known as an elementary function. Y prime is the derivative, and x cubed is our function. Now, the unknown function y is not included in this one because it's elementary, so it's a different type of differential equation. The next one, y prime equals xy, this one has both of our functions. We have an x and a y. Again, y prime is the derivative, and now this time we have an actual unknown function, y, which is assumed to be a function of x. And the last one, dy dx equals g of x f of y. This is in Leibniz notation. Dy dx is a derivative, g of x is a function of x, and then f of y is the unknown function. So it's just a different notation, basically saying the same thing. Moving on, to give a quick introduction to how we classify such equations. The main way is by their order. The order of a differential is the same as the highest order derivative it contains. So, some examples of this would be this. Second derivative, let me zoom in. The second derivative, right, d squared y over dx squared equals x squared minus 1 over y plus dy dx. So we have two different derivatives, a second order and a first order. Since second order is our biggest one over here, it is called a second order differential equation. And our next one, y prime 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 prime, the fourth derivative of y equals y times the third derivative of y minus 1. Obviously, again, this is our highest order derivative, so that is the order of our differential equation. Going back, we will start with the next question. How do we solve these? Because they have an unknown function. Short answer is, most differentials do not have a general solution, but some differential equations do have general solutions. Listen to the two that I will be going over today are separable equations and linear differentials. So let's move to that. So, first type of functions we discussed were elementary functions. These are of the form y prime equals f of x. And we already learned how to solve these a lot with integrals. So some example of these would be x to a power is the general solution is found by the power rule. Next is y prime equals sine of x, right? Memorized those a while ago. That's just cosine y equals cosine x. And lastly, y prime equals 2 e to the x, and y also equals 2 e to the x because it's an exponential equation. So the idea with these is that these are differential equations. So the same properties that we can use on these, integrating them, often are used in our other two versions. So next, we have separable equations. These are of the form dy dx or y prime equals a function of x and a function of y, g of x and f of y. These do have general solutions because they can be rearranged into integrable forms because the x's and y's can be isolated from each other. Just like in this, where our y is all on one side and our x's are all on the other side. So, quick example, y prime equals xy. We don't know what y is in terms of x, but if we move them all to the same side, like this, dy over y, we divide by y, and we multiply by dx. So we get dy over y equals x dx. And we can integrate both sides of the equation because we only have y's on this side and x's on this side. Moving on, we have y prime equals x squared times e to the y. Similar idea here, we divide by the e of y, or the e to the y, and multiplied by d of x to isolate the y's and isolate the x's on either side. And our last type of equation is our linear differentials. These are a bit more complicated, and they're of the form dy dx, or y prime, plus a function of x times y equals another function of x. These can also be put into an integrable form by multiplying both sides by the integrating factor, often denoted by I of x. Down here, our first example is y prime plus a half of y equals 2. So, the equation for the integrating factor is I of x equals e to the integral of f of x. So whatever function of x that is in front of the y, in this case 1 over x, is put up here, and then we solve that. So in this case, e to the integral of 1 over x is the same as e to the natural log of x. And e to the natural log of anything is just whatever the natural log is of. So that is x, simply x. Substituting them back in, we reverse product rule to get d of x, or d over d of the derivative of xy equals 2x, because we then multiply both sides by our I of x, and that puts them both in integrable forms. And next, we have y prime minus y equals 8 e to the x. Again, the integrating factor is e to the integral of f of x. In this case, we don't have an x here, but we do have a negative sign, and since our form is plus, then we know that x is negative 1 there. So we take the integral of negative 1, which is negative x, and so our integrating factor is e to the negative x. Multiplying both sides leads us to the derivative of e to the negative x times y equals 8, and that is integrable. So that is a quick crash course on solvable differential equations, and now we will move to our examples. The first example we'll be going over is an elementary function, just to go over the practice of what we are trying to do with these differential equations. So first we will identify our y's and our x's. In this case, y prime is our only y, x squared is our only x. In this case, y is assumed to just be 1. So because it is already in this form, right, we will convert it to dy dx. Let me zoom in. dy dx equals x squared, right? So we multiply both sides by dx to get all the y's on one side and the x's on the other side. Then we integrate both sides, integral of dy, integral of x squared dx. Remember, there's a 1 hiding in here, which is our y. Integral of 1 is just y, and our integral of x squared is our power rule, so x cubed over our exponent, which is 3. So this is the long way around, where we just earlier learned the power rule to simply get that. This is the kind of the theory behind it. Yeah. Our next example is the differential equation, y prime equals x squared over y. So again, we will identify our y's and our x's. In this case, we have a y over here, which we will have to move over, and our y prime over here, or dy dx. So first, let's multiply both sides by y. So we have, let me erase that. So first, we have dy dx equals x squared over y. We want to get the y to the other side, so we multiply by y on both sides, and we get y dy dx equals x squared. Now we got to get this x dx over here to the right side, so we're going to multiply this by dx, so times dx, and this will give us our separated equation of y dy equals x squared dx. Integrating both sides, right? Integrate this and integrate this. These are both power rules, y and x squared. So y is going to be y squared over 2, or 1/2 of y squared, and x is going to be x squared, or x cubed over 3, which equals 1/3 of x cubed. Because it is an indefinite integral, we must not forget to add c. So now we have to get this down to just a y. So what I want to do is multiply both sides by 2, which will give us y squared equals 2/3 of x cubed plus 2c. And then we want to take the square root of the whole thing, and that gives us our answer. Or before we do that, have a quick note to make. Y equals the square root of 2/3 of x cubed plus 2c. Because this is an arbitrary constant, it doesn't matter what coefficient is in front of it, so we can simplify our answer to y equals the square root 2/3 x cubed plus c. That is our final answer. Our next example is a linear differential, because we have y prime plus a function of x times y equals x, another function of x, in this case x squared plus 1. So because the y is not alone, we must get the y alone to get it into the correct form. So first, we will rearrange the equation to dy dx equals 2, or not equals, my bad, plus 2 over x times y equals x squared plus 1. Because now we have y isolated in a function of x right there. So now we must solve for the integration factor. We know I of x equals e to the integral of f of x dx. In this case, our f of x is 2 over x. So this equals e to the integral of 2 over x dx. We can take the constant out, and so that leaves us with the integral of 1 over x. So we take the constant out, put it in front, 2 integrals, 1 over x. That gives us the integral of 1 over x is ln of x, so we get e to the 2 ln of x. This cannot be broken down any further. We have to make one quick step. So there's a rule in logs where if anything is in front of the log, you can put it inside the log as a power. So we will simplify this to e to the ln of x squared. Now we have an e to the ln of something. So we know that that equals that something. So that is x squared in this case. Yeah. Cut that out. So now we multiply both sides by the integration factor. So we have x squared times dy dx plus 2 over x times y, and x squared times x squared plus 1. This gives us x squared times dy dx plus 2x, my mistake, plus 2xy equals x to the 4th plus x squared. Now this is not immediately differentiable. We know this side is, but we don't quite know what this is. So if we remember back from our first unit, the product rule, and if we invert that rule, we will find that the derivative of x squared y first, d second, in this case y prime or dy dx, plus second y times d first, which is 2x. And if we compare that with this, we have x squared dy dx and 2xy, and this is equivalent to 2xy. So we know this is equal to the derivative of x squared y. And now both sides are easily integrable. We know this one is simply cancel out the d dx, d over dx, and that gives us x squared y. And this one, the integral of this, is x to the 5th over the 5, x cubed over 3, and don't forget c. Divide both sides by x squared to get y alone, and that leaves us with y equals x cubed over 5 plus x over 3 plus c over x squared, and that is our answer.